So this is Jack Jackson. I'm back with my second video on double integrals, and we're going to be defining and approximating double integrals in this video. So, review from Cal 1, we have a definite integral of a real valued function of a single real variable, and it would be a good idea right now to maybe go back and review some videos from Calculus 1 that were found in my playlist, Unit 6 of Calculus, Definite Integral Concepts. We're going to provide a light review here as we go along. That might be sufficient if you remember this stuff pretty well, but if things are a little fuzzy for you there, I refer you back to those earlier videos. So what we're going to do, as always in Calculus 3, we're going to extend the Calculus 1 and 2 concepts, in this case the calculus concept of a definite integral, to what we call a double integral, and we're going to start with doing that over a rectangular domain. So let's start by reviewing a little bit of Calculus 1. So let's start with a function, let's say f of x, and for right now let's do one where the y values are all positive. So we got this function f of x here, and we're going to graph it from some a to b. In this case, the function is x times x minus 2 times x plus 3, and then add 4. And you get this polynomial function here, and then we're going to look at it between the integral between -3 and 1. And so that's a definite integral, and as you probably remember from Calculus 1 and 2, that this is an area here. Okay, so it's an area underneath the curve and above the x-axis between x equals -3 and x equals 1, or in general below f of x and above the x-axis from x equals a to x equals b. So the question is, how does this concept transfer to a function of two variables? Well, first of all, what's the graph look like? Well, instead of the graph being a curve, we know that graph is now a surface. Instead of the x-axis, we're going to have down here the xy plane. Instead of an interval here, we're going to have a rectangle. And instead of an area, we're going to have a volume. And that's exactly what we have here. So here's an example of, oops, let's go back. Here's an example of a curve. This one I'm going to be using for this example, for this video, and maybe the next one as well, is this function f of xy is 6 minus x squared minus 2y squared, which is this kind of tan-colored function here. And if we're going to integrate that over the rectangle, say x going from -2 to 0 and y going from -1 to 1, which is written this way in interval notation, or here it is over here in just inequalities. There's our function. And this makes a solid integral. Now I'm going to be using a lot of illustrations from GeoGebra, and there are some links right here in the slides to those to some of these things, and some other people have put these together. These aren't my creation. So Rasha Tarek is the one that came up with this one here. So let's look at, let's see if I can find that one. Here it is right here, and you can see the solid here. I'm going to recreate it here. So there's your function, and we're looking at it there. Somehow that top of that got cut off, but you can rotate that around here and kind of see what the solid looks like that we're looking at. That top should be shaded with the brown there as well. So here it is from the front. Here it is from the side. Here it is there. So let's see if we reset that, and one more time. We're looking at filling up underneath the surface down to the xy plane, and we're looking at filling that in with a solid thing. So what we're finding here is a volume. Okay? And that region, that rectangular region of the domain, is this rectangle R. That's the bottom of this surface here. Okay. So thinking back to Calculus 1, how do we start trying to approximate this area? This is kind of one of the main ideas of calculus, is to how do we find an area of some irregular shape? Easy enough to find the area of something like a rectangle with pre-calculus, but something like this requires us to use some calculus. Of course, this one here is this area is given by this integral. Well, if you remember, the first thing we did is we divided up this interval that's the domain, -3 to 1 in this case, into sub-intervals. They don't have to all be the same width, but usually we did divide them up into the same width. So here I've divided this up into 4 equal areas. All of them are equal, not equal areas, but equal lengths. And they all have size b minus a, which is this length, and then divide by n. So delta x is this width of each one of these, and where we've just divided that interval up. Then how would that relate to a double integral? Well, our domain that we're looking at is from -2 to 2 on the x's, and from -1 to 1 on the y's makes this rectangle right here. And so we have this rectangular region. Instead of breaking into when we break it into sub pieces, they are sub rectangles, not sub intervals this time, but sub rectangles. And let's say we divide n1 is the number of ways we divide up the horizontally. So this x interval is divided up into 2 pieces like this by drawing the vertical line here. And then n2 is the number of ways we divided up the y, which is also going to be 2. So we divide it right here on the y-axis, or the x-axis, y equals 0. And so we have 4 total, or 2 times 2, sub-rectangles. Notice that for each one of these, delta x is 1 and delta y is 1. So delta A, the area of each one, is delta x times delta y is 1 times 1 equals 1. So each one of these has a sub-area of 1. In general, delta x is b minus a over n1. If this is a here on the left side and b on the right side, and n1 is how many divisions we have going across sideways. So that's b minus a over n1 for your delta x. And delta y, if we make them all the same, we're going from c up to d, so that distance is d minus c. We're going to divide that into n2 pieces. So d minus c divided by n sub 2 is going to be delta y each time. Of course, the area is delta y times delta x. Now, once we divided this into sub-intervals here in Calculus 1, our next step was to make rectangles. And how do we find the height of the rectangle? Well, it was the same as the height of the curve. But of course, there are infinitely many different heights of a curve on a particular subinterval. And so, in fact, we can pick any one of the infinitely many x's between, say, -3 and -2 for this first interval, and use that, go up to the curve and find the height. And this one here, I happen to choose the left side every time. This leads to what we call the left Riemann sum. And so on this first interval, I go to the left side at -3, find the height, which is f of -3, which is this height right here. Looks like that's 4. Okay, of course I can find that by reading it off the graph here, or by plugging that -3 into the formula here. It's pretty easy to see. You get 4. -3 plus 3 is 0, so this all wipes out. And then you add 4 and you get 4 there. For the next one, I go to the left side of the interval, which is -2. Looks like that should be 12. I'll let you check that out to see that that works. Okay, and so forth. In a table, we're looking at going from -3 to -2 is one interval. Then from -2 to -1 is the second interval. From -1 to 0 is the third interval. And from 0 to 1 is the fourth interval. And each time we go to the left side. For the first interval, we'll use 4. The next one we'll use 12, then 10, and then 4, which are the heights of these 4 rectangles. Multiply each one of those by the widths, and now we get an area. I should say signed area, because these things right here might actually be negative numbers in some cases if the graph goes below the x-axis. Some of these would be negative, the rectangles would be going down, and they're going to actually subtract from the integral then because that area would be counted as a negative. Okay, so if we choose that, always go to the left side. There's an easy way to write this. Delta x is b minus a over n. That just makes sure that all your rectangles have the same base, the same width. And then the height is of an f value at some x sub k for the kth rectangle. K goes from 1 up to however many, whatever n is. So here's k is 1, 2, 3, and 4 is n here. So this is L sub 4 left Riemann sum rectangles. And to make sure that we're always at the left side, we do a plus k minus 1 delta x's. So if k is 1, you're just at a. K is 2, you add 1 delta x to a. K is 3, we add 2 delta x's, and so forth. And that makes that work out. So it's always at the left side. Find the f of that value, multiply by delta x. Now you have a signed height times a width, and that gives you the area of that one rectangle. Do this for all the rectangles and add them up. That's a left Riemann sum. You can see the details worked out here. And basically we're just adding these numbers 4, 12, 10, and 4, which are the 4 heights. We can factor out the common width of 1 if we want, or we can leave it in. If we leave it in, then each of these numbers here is actually the areas of those. In this case, that number is 1, so it didn't really the area and the height are the same number. And we add those up, and we get a left Riemann sum of 2. We could also do a right Riemann sum. This time we go to the right side of the interval. Everything is basically set up the same. The formula here looks the same. K equals 1 to n of f of x sub k times delta x. Delta x is still b minus a over n, so that we have equal width intervals. But this time x sub k is a plus k delta x's. So when k is 1, it's a plus 1 delta x, which puts you at the right side of here, negative 2 in this case. And then the next one, add another delta x for the next one, puts you at negative 1. And another one puts you at 0, and then at 1. And we're just finding the f values there, which turn out to be 12, 10, 4, and 0, which you see here in the table on the graph or by plugging in the formula. Multiply those all by 1, you get the areas of 12, 10, 4, and this last one degenerates just to a line segment, which has no area. And that adds up to 26. All right, so here's a question. How does this correspond to what we might be doing with a double integral? Well, an interval has 2 ends, but a rectangle has 4 endpoints. So there are going to be 4 things that are going to be similar to this. So here's your domain here. And we have our 4 sub-rectangles. And we could use a lower left estimate. So as we go along, say we go this one, this one, this one, and this one, working our way up, bigger x and y, we see that for this rectangle, we'll go to the lower left corner, which is negative 2, negative 1, and we'll evaluate that at the point here. Put in negative 2 for x, negative 1 for y. I'll let you work that out, and you should get 0, hopefully. Yep, that works out. Is 0. Negative 2, see here is becomes positive 4, so 6 minus 4 is 2. And then you plug in negative 1. Negative 1 squared is 1 times negative 2 is negative 2. 2 minus 2 is 0. So you do get a 0 above that, so that the surface is actually touching that point right there. So you take f of that value, which is 0, multiply by the area of that rectangle, which was 1, and you get the nothing above this. Okay. Do a similar thing here by plugging in the 3, which is what you get when you plug in this rectangle. Take the lower left corner here, which x is negative 1, y is negative 1, and plug that in the formula here, and you get 3 for the output. That's the height above the curve here. And do the same thing for these other 2 points, each time going to the lower left corner, and we get 10. What's this going to look like visually? Well, instead of being rectangles, these are going to be right rectangular prisms. You're going to have 4 little columns that are rectangles on the bottom. There'll be these rectangles over here that we had divided up on the bottom. And then the height is going to be the height above the correct point. So the height here is the lower left-hand corner, which is here, which is this one right here. So this one degenerates down to nothing. Just a square with no height. So that's no area, no volume, rather. Then the next one we did was here. That's going to turn out to have a volume of 3, a height of 3, and a volume of 3. That one is actually this one here in this corner. And so you moved over to this rectangle, do the one in the lower left. So the lower left here of this rectangle is this one right here. Remember the red axis here is the x-axis, the y-axis, and the green is the x-axis. Okay. And so we go above that. And you see the x is running from -2 to 0, and the y is running from -1 to 1. So we're looking at this point, we're looking at x is -1 and y is -1. Y is negative. Yeah, y is -1. So we're looking at that corner. Go up, and there's your rectangle right there. Okay. Actually, I think it's one in the back here. Excuse me. It's one back here in the back. That corner going up. This one right here is this one right here. It's the shorter one. It's in the front right here. This one's in the back. Is the taller one. Yeah, this one's in the front. It goes up here and makes this. It's a little harder to see what's going on here. Which one's in the front and back. But this is the one that's in the front. This is the one that's in the back. So that height right there is the 3. This one is the 2 right here. And that's at this point, which is x is -2, y is 0. Yeah, so that's right here. And the big one is this 5, which is x is -1, y is 0. Okay, and it's going to be back here. Let's see, right here. And that goes all the way up to here. Okay, this is another one you can see, another GeoGebra source that I'm borrowing from there. Okay, and by the way, big thank you to Greg Petrix and all the other authors that I'm using for these things. I think I have, yeah, here's the picture for his. Let me turn that off. And this one here, let's say, yeah, here's the picture here. I think I can turn this around so you can kind of see it a little bit better. So you can see the ones there. So you can kind of see the square there on the bottom, rectangle, and you can get a different, by looking at this moving around, you can get a feel for the different shapes, the different heights and things that we're looking at. Okay. Okay, we may come back to that in a minute. Okay, moving along. If we did something, so that was the lower left. Well, instead we can use the lower right. So on this first one here, we're going to use the lower right corner, which is x is -1, y is -1. So that's this one right here, height of 3. If For this one, we're going to use lower right. So we use this one. X is 0, Y is negative 1. That's going to give us a height of 4. Then we move up here. Lower right is here. So that's going to be X is negative 1, Y is 0. That's going to give us 5 for the height. And in this one here, lower right would be this one here, and so forth. That would be height of 6. Okay, similarly, we could do upper left. So in here, we can go the upper left here. And on this one, we're going to be using the height here of 2. Height in the upper left here is 5. Height in the upper left here is 0. And the height in the upper left is 3. Multiply those by the areas of the base, which is 1. And so we get areas above, or volumes above that of 2, 5, 0, and 3. Add those up, it's 10. And if you look, let's just review real fast. We had lower left was 10. Lower right was 18. Upper left was 10. And then we can also do upper right. So here, if we take the upper right corner, here, 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 and here. So this one was the upper right-hand corner, would be the 5. The upper right-hand corner here, take the Y value, would be 6. Upper right-hand corner here is this one. At X is negative 1, Y is 1. Height there is 4, and 3, and then 4 for the last one here. Multiply those by the area of the base. We get volumes above those of 5, 6, 3, and 4 for a total of 18. Okay. So those are analogous to the left and right Riemann sums that we did in Calculus 1. Now, in Calculus 1, we found that we could get a better estimate than the left or right Riemann sums by doing averaging the two. We call that our trapezoid estimate. So T sub n is L sub n plus R sub n divided by 2. And the reason we call that a trapezoid estimate is it is certainly a Riemann sum. It is a height of a rectangle whose height is an average between the heights of the left and right. So if you look at this first rectangle, it's supposed to have exactly the same base there. You'll see that the height at the left would be here at 4. The height of the right would be 12. If you average those, you get a height of 8 in between. So that would be this rectangle here. And similarly for the other 3 rectangles. Okay. Now, if we so we could do those individually like that. But we also could see that it's equivalent to the height or the area of a right trapezoid, where the trapezoid top is a secant line segment going from one end of the interval to the other end like this. And the reason why this works out is this little triangle here and this triangle here are congruent. We know that the height is halfway in between. So this length right there of the triangle from here to here is the same as the length here. They're both right angles here, and vertical angles are congruent. So the angle-angle side theorem from geometry says those two triangles are congruent. So we could cut off this piece here, flip it up there, rotate it around this point, and we get a trapezoid with equivalent area. So that's the trapezoid rule. And of course here we could do it just by averaging the left and right. 30 plus 26 divided by 2 is 28. Or we could figure it on each piece, 8, 11, 7, and 2, by averaging these and multiplying by the widths on each one to find the area of each piece, and then adding those up. Either way, you get 28. We can do something similar by averaging one or more of these corner estimates. This would be something analogous to the trapezoid rule. I'm going to average all 4 of them. So add up lower left estimate, lower right, upper left, and upper right, and divide by 4. I'm going to consider this my T estimate. So we had a two divisions by 2 divisions for a total of 4 rectangles. We saw earlier that lower left estimate was 2, lower right was 18, upper left is 10, upper right is 18. At this point, there's no reason to think that any one of these is particularly better than the others, so we just add up all 4 and divide by 4. and we get 14. Another way to do it would be to average the heights on each one. So if we look at this rectangle that has endpoints at these 4 points at these 4 points, these 4 corners, we find the y values at those 4 corners, which were 0, 2, 5, and 3. Average those. Let's say you add those up, that's 10, and divide by 4, that's 2.5. Multiply by the area of 1, that would be 2.5 for the area above that. And we do the same thing for each of the others, and we could work that out individually and get 14. Or if we've already done these lower left, lower right, and so forth, we can just average all of those. So that's analogous to the trapezoid rule and in the 1D or 2D case. Now, it turns out there's an even better way to do it in Cal 1, and that is to do the midpoint rule. So the midpoint rule is you take the interval, you find the x value in the middle of the interval, go up to the height of the curve, and draw your rectangles there. So these little blue rectangles should all be hitting at the same places here with the curve. Now, so that's areas of rectangles. It's a Riemann sum. Now, here I've expanded my table out to include the points in the middle, which are these 4 here, -2.5, -1.5, -0.5, and 1/2. Find the y values by plugging in the formula, whatever it was, and this is what they turn out to be here, in decimal form. Multiply those by the widths, which are just 1, so it's the same numbers. And each one of these is the areas of these 4 things. Add those up. In this case, we get 30. And that's the midpoint rule. Midpoint rule can be visualized as rectangles, just like all of the others, just like the trapezoid rule and so forth. But also like the trapezoid rule, it can be visualized as areas under right trapezoids. What you do here is you take the point in the middle, in the midpoint, above that where it hits the top of this rectangle hits this curve, which is right above the midpoint of the interval, and make a tangent line there to make the top of or tangent line segment to make the top of a right trapezoid. Turns out, once again, this triangle and this one here are congruent. The way we see it this time is we know that this is the midpoint, so the distance across here is the same as the distance across here. Congruent angles here are for vertical angles, and the right angles are congruent. So again, by angle, angle, side, we get these two, or I guess angle, side, angle this time. We get these 2 triangles are congruent, so we can cut off this part here, rotate it up, and put it up here, and we have a trapezoid area. So both cases, the trapezoid rule and the midpoint rule really can be thought of as approximating with trapezoids. The trapezoid rule is approximating with the top of the trapezoid being a secant line segment at both ends, and the midpoint rule is approximating with a tangent line segment in the middle. Now it turns out, if you look at the size of the error here. So like say right here, this is over by this much here and this much right in here. Take the same piece over here on the trapezoid rule, and it's under by this bigger amount, about roughly twice as big amount. And so we say that one's over when the other one's under, so that's we can average them and get something better. But we weight the midpoint more because it's a little bit better, usually about half the amount of error, roughly. And so we get something else. It's called Simpsons Rule. I'll come back to that in a minute. So let's see what the midpoint rule would look like for this one here. So here's this thing drawn out with the midpoint rule estimates. And what we do here is we take the right in the middle of the rectangle. That's where the 2 diagonals meet. So if you draw corner to corner and corner to corner with line segments, wherever they cross would be the centroid of that, or the center of that rectangle, and take that for our point. So in this first one, it would be -1.5 for x and negative 0.5 for y. That would be right here. And you evaluate the function. Turns out it's a height of 3.5. So that's above this midpoint here. The height is 3.5, which is right there. You also got the height of 3.5 above this one right here. That's back here. Midpoint of this rectangle back here. Go up. In the front here, this way here, are these two, and both of those have heights of 5.25. And so you're adding up those four volumes again, and in this case it's 17. So there's the midpoint estimate. Now Simpsons rule is an average of the trapezoid and the midpoint, but we weight the midpoint twice as much. So it's a trapezoid plus 2 midpoints and divide by 3. And we notice that if you take this, the labeling gets a little wacky in my opinion. We say if we take a trapezoid end and 2 midpoint ends, that's not Simpson end, but Simpson 2 end. I prefer to think of this one in this case as, say, 3 intervals, one from -3 to -2, another one from -2 to -1, -1 to 0, and 0 to 1. I guess it's four intervals actually. So I think of this, say, from -2 to -1 as being one interval where we use information from the left, the right, and the middle. The y values here, here, and here. But some people will think of that as being 2 intervals, but you treat the left and right sides differently. So in any event, most books will call this Simpsons 8, when it's the way I'm thinking of is 4 intervals. But in any event, you average it that way. Our numbers we had for midpoint was 30 and trapezoid 28. So you work that out. It's 29.3 repeated is the area there given by the Simpsons rule. We could do something analogous to that in the case over here. We have a trapezoid and midpoint rule, or something similar to the trapezoid and midpoint rules. And so this would give us a Simpsons rule over a 2x2, 2 divisions each way. This is using my way of dividing this up. And although I guess some people might call this 4x4. And that was 14. This was 17. 14 for the T estimate. That was the average of the ones at the 4 corners. Using the one at the midpoint was 17. Work those out in 16. Turns out, we'll see later on, that this is exactly 16, as we'll discuss a little bit later in the video. So here's a summary of the table of our data and our estimates here that we have so far. So that's what we have. Now taking any one of these, say if we just take the right Riemann sum, and we let n get bigger and bigger, n's 4 here, 8, 16, 32, 64, 128. It's starting to approach the actual area we're looking at. So we can make it exactly that if we take our limit as n approaches infinity and the delta x's approach 0. So one way to do this, a simplified version, is to always use a right Riemann sum with even delta x's. So all the delta x's are the same. That makes delta x b minus a over n. If we want it to be a right Riemann sum, we put xk equal to a plus k delta x. Then you take f of xk for a height times the common width of delta x. That gives you an area of one rectangle. Add that up for all the rectangles. That gives you your right Riemann sum. Take the limit as n goes to infinity, and automatically, because the way we defined it, delta x goes to 0, and that's actually the definite integral from a to b of f of x dx. In the notation, we can drop the subscript here. The delta x becomes the dx, and the sum, which is a Greek s, becomes this long skinny s, which we call an integral sign. Similar thing happens over here. And here this one has midpoint approximations. I think this is 2 by 2, and then I half each of those regions, well, quarter them, half it in each direction. So this is 2 divisions this way and 2 divisions this way. This is 4 by 4 divisions for 16 of these columns. This one is twice that, so it's 8 by 8, 64 here. This one's 16 and 16. And so you see all of the different rectangles there. It's getting closer and closer to the actual integral, which is that volume. I think I can do that here by showing you more and more and more here. You can see that getting closer and closer there. Smaller and smaller divisions here, closer and closer to the actual volume that we're looking for. So ultimately, we can define the definite integral of a function of two variables similar to the way we define the definite integral of a function of a single variable. So if the domain is a rectangle, say from A to B on X and C to D on Y, we partition it into n smaller rectangle regions so that they are non-overlapping and the union is all of R. Let X sub k, Y sub k be any point in the kth subrectangle. Let A sub k be the area of that kth rectangle. And then we define the double integral over that region of the function xy dA. It's defined to be equal to, well, you take the area of that subregion, delta A sub k, the representative point xk, yk within that, find the f value of that, which is your height, multiply those together, you got a volume of a rectangular column, right, rectangular prism. Sum all those up and let n go to infinity in such a way that all the delta a's go to 0 as well. One specific way to do this would be to always use the same size rectangles. Notice up here the rectangles didn't have to be the same size. And I didn't specify where to pick the point. It could be anywhere in there. If we wanted to do something similar to the definition I showed you before where we always use a right Riemann sum, we could use the upper right Riemann sum here. This way. So your region is, or your domain that you're integrating over is a rectangle from A to B on X and from C to D on Y. You let delta X be B minus A over M, delta Y be D minus C over M, so we're dividing them into M groups either way. N is M square now, so the M square things, subregions. X sub I is A plus I delta X, that will go to the right of it, and C plus J delta Y will put you at the upper part, so this will put you at the upper right. Delta A is delta X times delta Y, so multiplying those together you get this formula. And then the double integral is then same formula we had up here, but specifically this delta A sub k is the same every time, so we just call it delta A. And the X sub k, Y sub k is given by these formulas up here. And we can sum this up, and actually I need to adjust this just slightly. And I need to adjust this so that this is X sub I and Y sub j given by these formulas, and I think of this one sum is like a double sum here. And so that is your double integral. Okay. Now what if the region is not a square region? Okay, what do we do then? So suppose the region is, say, the interior, whoops, let's go back, interior, say, of this ellipse. Well, what we do is we just draw some rectangle, any rectangle really, that includes completely the domain here, and we define a new function, g of xy, that g of xy equals f of xy for any points within this domain inside the ellipse or on the ellipse. But if it's outside that, but inside this rectangle, g of x is 0. And then we just define the integral of f as the integral of g. So g of x equals f of xy for points in the domain D, that's inside of here. G of xy equals 0 for points in R that are not in D, 0 out here. So when you start doing your Riemann sums, and say we start dividing up rectangles out here, this is not going to add or subtract anything from the interval. if we have a region that's out here. Okay, and so ultimately, when you take the limit of all that, it's going to work out just fine. And there's your general definition of a double integral. So now we know what a double integral is. Come back with the other videos for how we can put this in action and look at related concepts.